Thank you, Fernando, for the invitation. Really happy to be part of this seminar. Hope to be soon there in Durham. So today I'm going to talk about this work that started in my PhD work at the University of Buenos Aires. Then a couple of years I didn't work in this topic, and then I finished this work this year, or improve it in order to make some applications in the topic of data analysis. I'm going to talk about this by the end of the talk. So yeah, I'm going to talk about a refinement of the classic discrete Morse theory and some applications in problems in low-dimensional topology and also in combinatorial group theory. So let's start. This is the outline of the talk. I will start with this open problem, the undiscarded conjecture, and every time I talk about this problem, I tell I talk about two different stories: a topological story and a algebraic story. And in the end, these two stories meet each other to build a single problem. Then I will show you how we can refine the classic discrete Morse theory in order to apply it in this problem. And then how can we apply these kind of methods in the study of representations. And finally, some concrete applications in this conjecture, related to this conjecture. So let's start with this problem. This is an open problem, a still open problem from the 60s. And the motivation of this problem was by that time open Poincaré conjecture. Many people was at that time studying this conjecture, and one of the researchers that was very interested in this conjecture was Henry Whitehead. Okay, and in order to understand the homotopy type of simplicial complexes and then CW complexes, he developed a very rich and interesting theory called the simple homotopy theory. And what he tried to understand is to understand homotopy type from a combinatorial point of view. So I will tell you, we will call briefly this theory. So the idea is, suppose that you have to find a CW complexes, and you want to understand if, or to decide if these two complexes are homotopy equivalent or not, from a combinatorial point of view. So what he proposed was a list of basic moves between the decomposition of the complexes that preserve the homotopy type of the complexes and try to describe every homotopy equivalence with these basic moves. The kind of move that he proposed is the notion of expansion or collapse. So you have an elementary collapse from a CW complex into another one if you have this situation in which the difference between K and L is basically a pair of two cells of, with consecutive dimension. And the idea here, they have to satisfy some condition on the characteristic maps, but basically what you need is that you have to attach these two cells in such a way that the cell of lower dimension is a sort of free face of the bigger one. And in that case, if you eliminate or remove this pair of cells, you don't change the homotopy type of, it doesn't change the homotopy type of the complex. And in general, you can perform many of these moves. So in general, you have a collapse or expansion when you have a sequence of these kind of moves. And in general, if you mix different kind of collapses or expansion, you have a deformation between two complexes. And this n here, an n deformation, is a deformation in which the complexes involved in the deformation has a dimension up to n. Okay, this is important in terms of the combinatorial complexity of this this deformation. Okay, and in general, we say that two complexes has the same homotopy type if there is an n deformation for some value of n. Okay, so a basic remark is that since every single elementary move doesn't change the homotopy type of the complexes, in particular, this every simple homotopy implies some homotopy. But what about the converse? Well, the converse is not true in general, and there is a K1 theory group that is called the Whitehead group that measures abstraction. Concretely, if the Whitehead group associated to a complex is trivial, then these two notions coincide, or what this means is that any homotopy equivalent is also a simple homotopy equivalent. Okay, or if you have two, if you have two complexes are, let's move this, sorry. Then any complex that is homotopy equivalent to K is also simple homotopy equivalent to K. Okay, and well, not every Whitehead group is trivial. There are some examples of constructions, but the good news is that for contractible complexes, the Whitehead group is zero. That's or equivalently, these notions coincide for contractible complex. So every time you have a contractible complex, you can find the formation of this complex in this way. And what about the dimension of this kind of deformations? Well, Whitehead in this sequel of works prove that if you have two n complexes, that these complexes of dimension n or less or equal than n, then if you have a simple homotopy equivalence, then you can find a sequence of moves in which the complex is involved has dimension less or equal than n plus 1. So you only need to increase the dimension of the complex by 1 in order to obtain this deformation. So this is to understand. So all these theories to understand homotopy equivalence from this combinatorial and elementary point of view. This is true for n different from 2, and for n equal to 2, this question is still open. So we don't know if you have two complexes, then you can find a free deformation between them. What was proved is in the 60s by CTC Wall that you can find 4 deformation. Okay. So this is from on the one hand, we have this open problem. On the other hand, we have this other problem posed by Andres Alcartis in the 60s. They were also interested in the Poincaré conjecture, and they proposed this this question. This question is in terms of group presentations, and they say that if you have a balanced presentation of the trivial group, this is a presentation with the same number of generator and relators, and the underlying group is the trivial group, then in that case, you can transform this presentation into this trivial presentation of the trivial group with the same relators and generators by a finite sequence of these 3 kind of transformations. In the set of the relator, you replace a relator by its inverse, or by the multiplication of another relator, or by a conjugate. Okay. And the interesting part, at least, so they propose this conjecture, and they prove some implications of this conjecture. If this conjecture is true, then it has some interesting consequences in terms of the 3 and 4 dimensional Poincaré conjecture. Yeah, and as you can see in the second consequence, they were looking for a counterexample of the three-dimensional Poincaré conjecture. In the end, any of these methods was used to prove the conjecture, but there's another interesting part of the article. This is the original article. You can see that it's very short. So they pose the conjecture and they prove some topological consequences. And there's a very interesting part of the article that is this part. This is a remark from the referee, the anonymous referee of this article. So a very huge part of the article is this remark. The referee proposed to the authors to consider a weaker version of their conjecture. Instead of considering only their moves, they suggest to consider also an additional kind of operation that is to add a new generator and a new relator and the inverse of this operation. A new generator Y and a new relator equal to the previous generator. Okay. And the referee says that this weaker version of the conjecture is equivalent to this open problem related to simple homotopy types in the case of contractible complexes. Okay, so here's where these two stories meet each other. So let's try to understand a little bit more this new this observation of the referee. So this kind of operations in representations are related to the Titzer theorem. Titzer theorem says that you can transform any presentation of a group into any other presentation of the same group by finding a sequence of the following operations. The first three operations are the operations proposed by Andrew and Curtis. In modern language, they are called Q-star transformations. The fourth operation is the operation that is proposed by the referee. And also we have this fifth operation that is not allowed in our context, okay? And something interesting is that the first four operations doesn't change the deficiency of the presentation. They said that the difference between number of generators and relators, but the last operation does, okay? And it's not allowed in our context. So if it's allowed, we know that we can transform our original presentation into the trivial, into any other presentation of the trivial. But what about to remove this operation, no? And let's try to understand a little bit, let's try to understand this observation of the referee. So we know that there is a close relationship between representations and CW complexes of dimension 2. To every representation, we can associate CW complex, is called the standard complex. This complex has a single cell of dimension 0. It's constructed in terms of the presentation. You have a cell of dimension 1 for each generator, and you have a cell of dimension 2 for each relator. And the touching map of these two cells is associated to the word that you read in the relator. Of course, here you need to orient your cells in order to make this construction. And the property that this complex satisfies that its fundamental group is the group represented by T. And conversely, to any complex of dimension 2, you can associate the presentation that is a presentation of its fundamental group. Here you use Van Kampen theorem, it's very easy. So you identify some spanning tree, the one skeleton, you collapse this spanning tree. At this point, you are not changing the homotopy type of K. And then this presentation is constructed as follows. So you have one generator for each cell of dimension 1 that's not in the spanning tree, and you have a cell, a relator for each cell of dimension 2. And yeah, you are reading the attaching map in this generator. You're describing the attaching maps in this in the relator. Okay. Under this correspondence, balanced presentations of the trivial group are in correspondence with contractibility complex. This is a consequence of a very easy computation of related to Euler characteristic. And here we use the Whitehead theorem that characterize contractible complexes in terms of the fundamental group and the homology group. So it's you only need to compute. If you want to prove that the CW complex is contractible, then you only need to prove that it's simple connected and the higher dimensional homology groups are trivial, and then you know that it's contractible. And last but not least, this is the observation of the referee. The Q star transformations, 4 transformations, and at the level of group presentations are in correspondence with 3 deformations. This observation of the referee was formalized in the 70s by an article by Wright. So at this point, we have 2 equivalent open problems, 2 equivalent conjectures or versions of the Anders-Cartes conjecture. The geometric version that says that any contractible 2 complex predeforms to a point. This is the case n equal to 2 of the open question of Whitehead for contractible complexes. And this is a weaker version of the Anders-Cartes conjecture proposed by the referee that says that any balanced presentation of the trivial group can be transformed into the empty presentation by a finite sequence of this extended list of transformation that is called now Q star transformation. And what about this conjecture today? It's believed that it's false, but it's still open. There are some classes of complexes for which the conjecture is supposed to be true. From a computational point of view, it was proved that there is a super exponential. So there exist some complexes for which you need a super exponential length of simplification sequences. In 2015, Britson showed some examples of group presentations for which balanced presentations of the trivial group that satisfy the Anders-Cartes conjecture, but the lower bound on the number of movements that you need in order to trivialize it is super exponential in some parameters that define the presentation. However, there are many articles that try to solve this problem from an algorithmic point of view. And what they propose are some algorithms to explore the exhibits, a list of possible transformations. And of course, they work only in very small examples. They don't consider the new transformation proposed by the referee because from a computational point of view, it's hard to increase the number of generators or relators. Okay, so they preserve the number of relators and generator and explore all the possibilities in some smart way. And with these ideas, they prove that all the balanced presentations of the trivial group that are small in the sense that the total length of relators is less or equal than 14, then all these presentations satisfy the Anders-Cartes conjecture. So for small presentations, the Anders-Cartes conjecture is true. And there is a list of the so-called potential counterexamples of the conjecture. This is a list of balanced presentations of the trivial group for which there is not known any sequence of Q star transformation to trivialize them. Okay, these are some of the examples of this list is longer. And we're going to study this list of these potential counterexamples and in the end of the talk. So these are like some smaller open problems related to the conjecture. To try to prove or develop some methods to prove that these examples satisfy the conjecture. Okay, is there any question? Okay, so now I will. So I started to think in this problem in my PhD, and I wanted to face this problem from a different point of view first, to make new things, and I tried to use discrete Morse theory. So discrete Morse theory is about trying to understand homotopy types of cell complexes. So the first disadvantage is that it doesn't give you information about the simple homotopy type of the complex. So I will show you how to refine this the theory in order to make it applicable to the problem. So I will start with a brief summary of the basics on discrete theory and then how to improve it. So discrete theory is a combinatorial analog of the classical Morse theory for topological manifolds. And it was developed by Forman in the 90s. So suppose that you have a complex. In this case, you need the complex to be a regular complex. It's a complex where the attaching maps are homeomorphism. In particular, every simplicial complex is a regular CW complex. So again, this theory is based on the basic notion of Morse function. In this case, in this combinatorial setting, the Morse function is basically labeling on the set of cells. And this labeling has satisfied that for each cell, the number of faces and cofaces for which the value of f does not increase with the dimension is at most 1. Okay. So basically, if you label according to the dimension, this is a Morse function. And here I have an example of another Morse function. And there are some cells that are important in terms of this Morse function, and that are the critical cells. So n cell is, say, critical cells of index n if the values of f for which every face and coface does not increase with dimension is 0. So here you have two options, 0, 1. In the cases in which this value is 0, so every face and coface increase, the value of f increase with the dimension, this is a critical cell. So in the case when you label according to the dimension, every cell is critical, is a critical cell. And here we have in orange the critical cells. And we're going to see that the less the number of critical cells, the better in terms of the description of the homotopy type of cell. There is a combinatorial way to understand Morse functions, discrete Morse functions, that is in terms of pairings of cells in the complex. So every Morse function, every time you have this less or equal than 1, then you can pair cells. If you make some matching of cells in such a way that there is some acyclicity condition that is satisfied, then you can infer some Morse function. So there is some combinatorial way to describe Morse function. And well, this is a main theorem in discrete Morse theory. So you need the complex, a regular complex. You want to understand its homotopy type. You define some discrete Morse function, and then we're going to the last item of the theorem. The theorem says that K is homotopy equivalent to a new CW complex with exactly one cell of dimension K for each critical cell of index K. Okay. And in terms of proof this item of the theorem, there is an intermediate construction that is called the levels of complex of K. So suppose that you have some number, the levels of complex is the subcomplex of K of closed cells, with the value of F is less or equal than the real number. So what you have is that every time you are going to a non-critical cell, you don't change the homotopy type, but every time you have a critical cell, then you change the homotopy type. This is the main idea. So in our example, this is our regular complex. This is a labeling. These are the critical cells. And the idea is that if you use this theorem, you can deduce that the original complex has the same homotopy type of the new complex that has a single cell of dimension 0, two cells of dimension 1, and a cell of dimension 2. Even though you have a description of the incidence numbers of the critical cells into the lower dimensional critical cell, this is not enough to describe completely the homotopy type of the original complex. Okay, and here's a picture of this process of this filtration of complex induced by the levels of complexes. Each time you go through a critical cell, you change the homotopy type, and every time you go through cells that are not critical, you're not changing the homotopy type. So at this point, we have two goals to try to apply this theory in order to reconstruct simple homotopy types. The first goal is to try to reconstruct concretely the most complex, this new complex that you simplify or you obtain after the simplification of the original complex using only the critical cells. And the second and most important part is to well, both are important, but this is important in terms of applying this theory in our context. We need to recover information not only about the homotopy type, but about the simple homotopy type of K. And moreover, about we need bounds in the deformation. Okay. So the first things to observe is that you really don't need the exact the discrete Morse function. So this process of transformation of the original complex is completely described by this sequence of subcomplexes, levels of complexes. So it's the same, it's equivalent to have a discrete Morse function with some set of critical cells, and to have a filtration of complexes, a filtration of K, in which you have either a collapse or you attach new cells, and the cells that you attach are a set of critical cells. So in order to describe this process of transformation of K, you only need this description of this filtration of K. So let's go to the picture. So in order to reconstruct this Morse complex, this Morse CW complex, we need to pay attention to this situation when you go through a critical cell. So suppose you are in a very simple situation when you have a collapse and then you attach a new cell. So in that case, if the dimension of the complex is less or equal than n, then there is an n+1 deformation from the original complex, this K, plus this new cell, into this complex L, that is the original, into this complex L plus a new cell that is attached with a new attaching map, that is a composition of the original attaching map and the strong deformation retract induced by a collapse. Every time you have a collapse, you have a strong deformation retract, and you compute this composition. And the most important thing is that here you have an n+1 deformation. This is called an internal collapse. So you have a collapse and then you attach new cells. You have an internal collapse between these two new complexes. In the general case, the thing is much more complicated because you have, this is the sequence of levels of complexes. in the setting of Morse, discrete Morse theory, you have a sequence of many collapses and many cells attached at each time, and then this procedure you repeat several times. Maybe, okay, so in the general case, we have a much more complex situation. So this is a result that is, it's not difficult to prove, but it's very technical because you need to be really careful in this dimension. So what I prove is that you have this filtration, you have either a collapse or you add new cells. Then if you have this set of new cells that you attach at each step, then K is n+1 deforms to this new complex that is computed from the smaller complex in this filtration, and then you attach all these cells that that are part of this process at every step. You attach all the cells, and you can reconstruct inductively the attaching map. Okay. So there is a concrete description of the attaching map of these cells. It's similar to the previous case, but a little bit more technical. So putting it together, you have this new version of the Morse of the classical theorem in discrete Morse theory. If you have a complex of dimension k, which is regular, and a discrete Morse function, then F induces filtration of the complex K, where either you have a collapse or you attach new cells. This is the set of critical cells. And then you have this n+1 deformation from the original complex into this new complex, in which you perform all these internal collapses. So you have collapses, and then you track how the attaching map of the rest of the cells of the critical cells change. And it turns out that this is the complex, the Morse complex, the Morse CW complex. So in the case of n equal to 2, you can track the free deformation class, or you have a new member of the same free deformation class of K. Okay. Right. Here's a picture of what's happening, a very simple example. This is a case of the torus. In orange, the critical cells, you have some labelings. Every time you have an arrow, you have the same label. The two cells, this one cell and two cells has a value of 13. So every time you perform an internal collapse, you track the evolution of the new attaching map. This is, you can be sure that at every step you preserve the free deformation class. So this is the Morse CW complex associated with this original complex. If you use this Morse function, and you can see that this is a minimal CW decomposition of the torus. Okay. This is a very simple example that tells you how to understand in a different way, using Morse theory, the free deformation class of some complex. Okay. How to use it in combinatorial with problems. So the pipeline was the following. You start with the presentation. You compute the associated standard complex. You compute the barycentric subdivision in order to work with regular complexes. Of course, you are not changing the homotopy type, neither the three-dimensional homotopy type. You compute some more function, and then you compute the associated Morse complex, the simplification of the original complex. And then you compute the associated presentation to this new complex. We proved that at the level of complexes, there is a free deformation. So this is the observation of the referee. At the level of presentation, you have few star-star transformation. Okay. And the good news is that we have an algorithm that takes as input the presentation and gives us output this new presentation. So you have the presentation, you can propose a Morse function, or the algorithm can compute randomly a Morse function over this complex, then and gives us output this new presentation in the same class. So this is a new way to generate presentations in the same class as the original that is not highly non-trivial, because we are not exploring the possible Q-structure transformation from the original one. So there is this, you have this underlying topological argument at this level to make this construction. So we'll explain in a very simple example how these algorithms work. Of course, we have a program to compute these transformations, but the procedure is as follows. So you start with the presentation, you compute the associated CW complex, the standard complex. Here is the barycentric subdivision. So this is a two-cell associated to the relator x to the square, and this is the relator associated to the sorry, this is the two-cell associated to the relator x and y to the -2. Here it's very important to set some orientation in your cells, and then you compute some Morse function. And as I told you, there is a combinatorial way to describe Morse function in terms of acyclic matchings in the set of cells. Then the algorithm works as follows. So you start with a very, you can construct a very huge presentation at the beginning. So you have a presentation with a cell for each, sorry, with the generator for each cell of dimension 1 in this complex, and you have a relator for each cell of dimension 2 describing the attaching map, and also you have a relator for each cell of dimension 1 that is not critical. And then, of course, you can remove this pair of generators and relator because they are the same. This is a fourth operation proposed by the referee. And this is equivalent to collapse and spanning tree in the level of the complex, this step. Now, let's perform the internal collapse in dimension 2. So every time you have a pair of cells that are not critical of dimension 2 and 1, you have this generator and this relator. And the condition of being a Morse function ensures that this generator only appears once in this relator at every step of this procedure. So you can rewrite this generator in terms of the rest of the relator, and then replace it in the rest of the relators, and then remove this generator and this relator. This is the new presentation that you obtain. And this is the same, or this is the same what is happening at the level of complexes when you are transforming or deforming the attaching maps of the original attached maps. Okay, this is what's happening at the level of presentation. So again, here you have this internal collapse, so you rewrite its routine in terms of the rest of the relator, and then replace in the rest of the relators, and then remove this pair of generator and relator. So you continue with this procedure, and then in the end you obtain until you don't have any pair of cells that are not critical, and in the end you have a new presentation in the same Q star class than the original one. So this process simulates what's happening at the topological level when you perform all these internal collapses. Of course, this is a very simple example, but we try to apply this method in trying to understand the potential contour examples of the conjecture, and we prove that all these potential contour examples indeed satisfy the conjecture. So here we have some concrete examples, and the procedure is the same I showed you before. So you have this presentation, you generate randomly a Morse function, and in a couple of tries, you obtain a new presentation that is very easy to trivialize using Q star transformation. The last example is a infinite family of examples. So here we use an inductive reasoning, and something interesting is that this method is not limited by the size of the presentation. You can use this method in any presentation, and the complexity of the computation depends only on, so it's linear in the number of the total length of the relator, so it's very easy to compute this transformation. Yeah, of course, there are many other examples that we couldn't prove that satisfy the conjecture because we couldn't find a good Morse function that is useful in order to trivialize the presentation.
I think there's a question.
Yes.
So, am I understanding correctly that here you want a discrete Morse function with one critical point? Is that right?
Yeah. No, you're right with the question. So I find a Morse function, and what's happening in the I'll try to show you. So what's happening is, let's in the meantime look for the paper. We find some Morse function, and what you have is a new presentation that it's huge, but it's very easy to trivialize it using. So there is an algorithm that uses a greedy algorithm that try to trivialize a presentation using Q star move. Okay, indeed you use only Q star moves. So the idea is to transform this presentation P in another presentation, and when you use this greedy algorithm, you can trivialize it. So you have two steps. From P, you go to a new presentation. The Morse function perhaps has many critical cells. You have a new presentation that in general is big, but then this greedy algorithm can trivialize it. Okay, so this is the idea. So here I have some example. Let me find it. This is an example that I show you, but
I guess the follow-up is, do you know of a contractible 2 complex that's provably doesn't have a discrete Morse function with one critical point?
I couldn't hear you. Could you repeat the question? Sorry.
I don't know if you know of a contractible 2 complex that doesn't have a discrete Morse function with one critical point. Is it possible you can always find is it possible that if the complex is contractible, you can always find a Morse function with one critical point? I guess the answer is no, but I want to know what the counterexample is.
No, yeah. So in general, we don't have a Morse function with only a critical point in these cases. We have Morse functions with several critical points, but this new presentation that we build is very easy to trivialize. But in general, we don't have a Morse function with a single critical site. Yeah, I am looking for the example, but in general, you have very big new presentations associated with the original one.
Thank you.
Yeah, so in general, these the complexes associated to this presentation are not too big, so we can generate all the Morse function. And it's not true in general that you can find a Morse function with a single cell of dimension 0. Yeah, but that was the end of the talk. Here are some references. The starting point of this problem, of the study of this problem, was in my PhD thesis. I have this preprint that I showed you a couple of minutes ago. We made some code to compute this new presentation associated with the original one, and most of these algorithms are based on posets or finite topological spaces. We have code in Sage and also in GAP. And I know who was talking, but who made the question, but this greedy algorithm that I mentioned before is developed in GAP. So in GAP, you have a presentation and you can compute a reduction of this presentation. This is a greedy algorithm based on some paper. It's a smart greedy algorithm. So if you apply this algorithm in this presentation, of course, anything happens. So you still have the same presentation. If you compute this new presentation in the same class using more theory, then you apply this greedy algorithm that uses Q-star transformation, then you can trivialize it. So this is also useful if you have a presentation. Of course, in terms of computability, you cannot know if your presentation corresponds to the trivial group or not. But there are some algorithms that try to unveil and some easy examples, some concrete examples, if it corresponds to the trivial group or not. So if you use this basic algorithm, in many cases, you don't know if your group corresponds to a trivial group. If you use this new algorithm that is more flexible because you can choose a more randomly a Morse function, or you can propose a Morse function, then in all the previous cases, you can prove that in particular your group corresponds to the trivial group. So the proof that these groups correspond to the trivial group is in general geometrical. It's not just making some computation with the transformations in the group. And now I'm working in an application of these ideas in the computation or inference of fundamental group of topological spaces from finite samples. So in general, in topological data analysis, we have a finite sample of the topological space, and we aim to understand its homotopy type. And in particular, we are interested in the inference of homology on fundamental group and in general any other invariant. So there is a successful theory that is called persistent homology that infers homology groups from of a topological space from a sample, but there's not much more work done in terms of the fundamental group, because of course it's more difficult because you are dealing with representations and you have this problem of the isomorphism problem. But yeah, we have some ideas in this direction. And this is all I wanted to say. Thank you for your attention. I'm open to questions.
Thank you very much, Ximena. So